Hey everyone, and welcome to our explainer today. If you're tuning in, there's a good chance you might be neck deep in your electrical engineering studies right now, maybe staring down a looming exam and just feeling the weight of all those complex formulas. If that's you, I want you to just take a slow, deep breath. Today, we're stepping away from the high-stress lecture hall. Instead, we're going to take a gentle, unhurried journey into circuit analysis. We're going to look closely at the underlying, peaceful harmony of electricity.
Section 1, the magic behind the wires. Okay, let's dive into this. We're going to start by completely stripping away the noise and focusing on the core concepts that literally make up every electrical network in existence.
I mean, have you ever looked at a complex circuit, the ones just drowning in second-order differential equations and transient responses, and felt an instant wave of panic? It's incredibly common, especially for college students. Your textbook presents it as this chaotic math problem you have to somehow solve. But I want to assure you, right here and now, that we're going to take the panic entirely out of the math today. We're not going to grind through endless calculations. We're just going to look at some very simple, very natural behaviors.
Because beneath all that dense textbook math, circuits are actually just an elegant choreography of energy. Whether it's the smartphone in your hand right now or the massive power grid lighting up a whole city, the devices powering our world are ultimately just combinations of three simple physical actors. And you know what the beautiful part is? They play by extremely patient, completely predictable rules. If you can just understand their individual personalities, the whole system makes perfect sense.
Moving on to Section 2. Meet the three components. Let's get to know these three basic elements. Try to think of them not as abstract variables on a chalkboard, but as old, reliable friends that you're just getting to know.
First up, we have the resistor, denoted by the letter R. By definition, it's a passive element that doesn't supply energy, but rather dissipates it. Think of the resistor using a very gentle analogy. It's kind of like friction on a physical stage. It takes the kinetic energy of the electrical current and it just burns it off, usually as heat, so that things don't spiral out of control. It's really the stabilizing force that keeps the energy flow grounded.
Next is the capacitor, or C. This is also a passive element, but instead of burning off energy, it actually stores it in an electric field. You can picture the capacitor calmly as a water tank, or maybe a flexible spring. When voltage is applied, it fills up, storing that energy for later. And once it's completely full, what we call the steady state, it simply blocks any more current from flowing, acting entirely like an open circuit. It naturally resists sudden changes in voltage by basically absorbing the impact.
Finally, we have the inductor, or L. Like the capacitor, it stores energy, but it does so in a magnetic field created by current flow. Now, what's really interesting here is how the inductor behaves compared to the capacitor. Think of the inductor as a heavy, spinning flywheel. It takes some time to get it spinning, but once it's moving, it really wants to keep moving. It naturally resists changes in current. And once it reaches a steady state under a direct current, well, that flywheel is spinning effortlessly, acting just like a short circuit, letting current flow freely without resistance.
And if we pull it all together in this summary, we can see our entire cast of characters in one peaceful view. The resistor dissipates, the capacitor stores and opens, the inductor stores and shorts. By simply keeping this steady, predictable table in mind, you have the keys to unlock almost any circuit problem. These three simple building blocks just have perfectly predictable personalities when they're left alone to do their jobs.
Section 3. The rules of the road. Now that we know exactly who is on our stage, we need to understand the simple rules that govern these components when they actually share the same circuit. There are really only two fundamental laws you need to remember.
Take a look at this beautiful page of handwritten student notes covering Kirchhoff's current law, or KCL. Honestly, seeing handwritten notes is kind of reassuring, isn't it? It reminds us that generations of students have sat exactly where you are and mastered this stuff. KCL simply states that the algebraic sum of currents meeting at a node equals zero. Put even more peacefully, what flows in must flow out. Electricity is just a continuous stream. Absolutely no energy is magically lost at a junction. It just takes different paths.
And here we have notes on Kirchhoff's voltage law, or KVL. This law tells us that the algebraic sum of voltages around a closed circuit loop must be zero. So the crucial point is that as you walk in a circle around any loop in a circuit, whatever energy is supplied by your battery or your source is exactly matched by the energy dropped across your components, like resistors. It's a perfectly balanced scale. Nothing is wasted, and nothing just appears out of nowhere. Section 4. Teaming up. RL and RC. So, with our components and our rules firmly established, we can begin to see what happens when these parts start interacting. We're going to look at some simple pairings first, keeping our focus firmly on intuition over math.
Here we have a circuit combining a resistor and an inductor, an RL circuit. When you throw the switch, the math tells a really fascinating story. Notice the handwritten curve here. See how the current doesn't just instantly snap to its maximum value in a harsh, jagged line? Instead, it traces a smooth, gentle, exponential climb. That is our inductor at work. Its flywheel effect is actively resisting that sudden rush of current, building up momentum gracefully over time.
Now, textbooks love to use terms that can sound intimidating, so let's just break them down peacefully. The natural response is literally just how the circuit relaxes when you take the battery away. It's just the components releasing their stored energy. The forced response is how the circuit behaves when it's being pushed to work by a continuous source. And the time constant, denoted by the Greek letter tau, is basically just the circuit's natural speed limit. For an RL circuit, it's L divided by R. For an RC circuit, it's R times C. It simply tells us how long that gentle curve takes to finally flatten out.
And this brilliantly illustrates exactly what we're talking about. Here we see an RC circuit, a resistor and a capacitor, that has had its power source removed. The math clearly tells us that the voltage drops to exactly 36.8% of its initial value in exactly one time constant. So what's happening in reality? The water tank of the capacitor is slowly, steadily draining its stored energy through the friction of the resistor. The energy just fades away smoothly, returning the whole circuit to a state of calm.
Which brings us to Section 5, the RLC symphony. Now we are totally ready for the final combination. What happens when you put all three, the resistor, the inductor, and the capacitor, together? It's so often framed as this terrifying second-order differential equation, but I really want you to see it as a beautiful collaboration. Let's see how this builds when we actually combine these elements. Notice the physical circuit diagrams showing both series and parallel combinations, and right alongside them, the mathematical result showing sines and cosines. So why does sine waves suddenly appear? Because you have a spring, the capacitor, and a flywheel, the inductor. They are playfully trading energy back and forth, creating a gentle, rhythmic oscillation. This is literally the very foundation of single-phase alternating current, or AC circuits.
I want to reassure you that all the scary calculus we just touched on really just describes this, a peaceful pendulum swinging. The energy swings back and forth between the inductor and the capacitor, but because the resistor is there providing that gentle friction we talked about, the swinging doesn't go on forever. It slowly, safely dampens the movement, eventually bringing the entire electrical symphony to a quiet, steady rest.
Section 6, your peaceful takeaway. As we start to wrap up this explainer, I want to offer a quick mental reset. If you came into this feeling the immense pressure of your engineering studies, I want you to just let that go for a second.
As you've seen, complex circuits are absolutely not chaotic, random math problems designed to trick you on a test. They are simply basic components following very patient, highly predictable rules. If you can just understand the friction of the resistor, the spring-like storage of the capacitor, and the flywheel momentum of the inductor, then you understand the very heart of electrical engineering. All that math is just the language we use to describe this incredible natural harmony. So, I want to leave you with this final thought. The next time you open your textbook and stare down a sprawling, daunting circuit diagram, try not to see a wall of impossible equations. Look closer. Can you see the hidden, peaceful flow of energy, gently moving between components, just waiting for you to understand it? Thank you so much for taking this time to learn with me today. Keep that clear, calm mind, and you are going to do absolutely great.